Good evening. So this is Tom Herbert from The Useful Coach. And today I wanted to basically produce a short video with slides that's based on my article that I wrote for my website, useful.coach, called Nutrition for Soft Tissue Training, Recovery, and Injury Prevention. And the article will be continually developed, but it's long, and a lot of people don't read long articles. So one of the big things from the article I wanted to do was to share the new research on supplementation of collagen or gelatin in the acute training period, and why that's what I say here, a cheap and potentially effective nutritional practice for augmenting tendon and ligament strength and recovery. Let me just go into it. So collagen and tendons are ubiquitous in the body. But before I get there, I want to, what I say, a tale of two cocktails. And much of this research that's come about has come out of a lab from Professor Keith Barr. Now, Keith Barr is he's a professor of the Functional Molecular Biology Laboratory in UC Davis. And he's done a lot of work in the last few years on collagen synthesis. And I actually emailed him back in October 2016 before I wrote my article, just to answer some questions on various bits and pieces, and then wrote my article out of that, plus bits and pieces of research. So yeah, let's get started. So in about 2005, Dr. Barr's lab wrote a paper called, released a paper called The Exercise-Induced Biochemical Milieu Enhances Collagen Content and Tensile Strength of Engineered Ligaments. And the purpose of the study, as they say, was to determine the effect of the human exercise-induced biochemical milieu on collagen turnover using ligaments engineered from cells obtained from the human anterior cruciate ligament. So that's in your knee. That's the one that everybody breaks. We used a within-subject design whereby culture medium was enriched with serum obtained at rest and after exercise from the same individual. So basically, what they did, the scientists grew donated knee ligaments in the lab, and they bathed them in the blood serum drawn from individuals about 15 minutes after they're doing resistance training. So they were leg supersets. And then they compared the knee ligaments to those bathed in blood serum drawn from the same subjects at rest. So you can imagine these were ligaments. They extracted the ligaments and then bathed them both in serum that were drawn from the subjects, but the subjects were drawn after exercise and during rest. And basically they wanted to investigate whether there was an exercise-induced circulating hormones and nutrients that would aid in the collagen remodeling of the ligament. So what did they find? In summary, and this is me quoting here, we report that the ligament constructs treated for 7 days with a serum obtained post-exercise exhibit enhanced collagen content and tensile strength compared with constructs treated with serum obtained from the same individual at rest. Thus, our data suggests that one biological function of the exercise-induced biochemical milieu may be to support connective tissue remodeling. And they have another one here saying, from an applied standpoint, our findings suggest that changes in the physiological milieu may provide a signal to stimulate collagen turnover in tendon, ligaments, and skin to maintain or improve tissue function. Now, they also subjected these ligaments to two isolated, typically elevated post-exercise hormones. So that's growth hormone and something called IGF-1, insulin-like growth factor 1, which you hear a lot about recently because of its connection with protein and growth of cells, runaway growth of cells like cancers and things. But that's a whole nother slide. But what they found is that it didn't actually work as well as the blood serum. So they gave these isolated ligaments these hormones, right? These these hormones are normally elevated post-exercise, and these actually didn't affect the growth of the ligaments. And so they say here in another, well, this is in a 2016 commentary paper on this paper that we're talking about. There was, they said that basically, given the recombinant IGF-1 and G growth hormone showed no benefit for collagen beyond resting levels. The data presented by West et al., so this is the West, the paper, 2015 paper we're talking about, highlight the apparent importance of the complete physiological cocktail of the post-exercise milieu, where ultimately contains additional unidentified exercise-induced metabolites, hormones, binding proteins, etc., that may synergistically aid in remodeling of collagen tissue. And they also go on to say that the results from the present study, that's the West one, would suggest that it may be beneficial for athletes or the elderly, aiming to rapidly and effectively recover from musculoskeletal injuries, e.g. strains, sprains, surgeries, resulting from damage to the collagenous tissue, to engage in exercise with uninjured tissues in effort to induce transient increases in endogenous anabolic hormones. So this very briefly, these two papers, or the paper and then the commentary, was pointing to the fact that as we're training and our muscles are being used, our body is producing hormones and other biological chemicals, which they call this physiological cocktail of the post-exercise milieu, that actually appears to benefit the growth and recovery of tendons and ligaments. And these are not just the exercised ones. So that's the first thing to think about. And I put here in my article that actually this is something to think about in terms of the importance of resistance training, so loaded training outside of climbing, but more so training around damaged tissues. So if you have damaged your fingers in any way or any other ligaments, do carry on training around that. So we have a second cocktail in my story of two cocktails. And this is the nutrition-induced biochemical cocktail. And this is the big one that really pushed the article and is also really being used a lot in sports nutrition application at the moment. And this was the second paper from Keith Barr's lab. And this was a 2016 paper titled Vitamin C Enriched Gelatin Supplementation Prior to Intermittent Activity Augments Collagen Synthesis. And the background on the objective of this research is as follows. So musculoskeletal injuries are the most common complaint in active populations. Greater than 50% of all injuries in sports can be classified as sprains, strains, ruptures, or breaks of the musculoskeletal tissues. Nutritional and/or exercise interventions that increase collagen synthesis and strengthen these tissues could have a significant effect on injury rates. This study was designed to determine whether gelatin supplementation could increase collagen synthesis. So in this paper, the scientists continued in a similar way and as the previous study, the West one earlier. And so they used these engineered ligaments again, and then they subjected the tissues to blood drawn from subjects who were supplemented with various amounts, placebo, 5 grams or 15 grams of gelatin, and then equal amounts of ascorbic acid, so that's vitamin C, 1 hour before completing 6 minutes of rope skipping. And then this protocol was repeated 3 times a day for 3 days. And so basically they were tending to test the hypothesis that consuming gelatin, so gelatin is a food derivative of collagen, and I'll get into that, and vitamin C, which is a cofactor for collagen formation, is combined with exercise may increase collagen synthesis. So to test this hypothesis, to test this hypothesis, 8 healthy males will complete a randomized crossover design protocol where they will consume either a drink containing an isocaloric placebo, 15 grams of collagen or gelatin at a constant level of vitamin C, and then they'll measure the amino acids appearance in the blood, and then basically they'll look at the blood draws and see the effect of this on the engineered ligaments. So In the first paper, they looked at, they had donated ligaments, they exercised people, they then took the blood, sorry, they then took the blood from the exercising individuals and put that blood serum onto the ligaments and watched the difference between the growth of this post-exercise physiological cocktail milieu and the blood serum from those at rest. And what did they see? They saw that the ligaments grew better with the post-exercise blood. In this study, this 2016 study, Barr's lab did a similar thing, but what they did is they supplemented people who were exercising with various amounts of gelatin or a placebo, and then drew the blood post-exercise and put it onto the ligaments. So what we have now is we have the ligaments not only bathed in a post-exercise cocktail, but also in a post-exercise cocktail with supplemented gelatin acutely before the training protocol. And the reason that is because basically the amino acids, so these are the building blocks of the protein, and collagen in your body is made out of proteins, is high in these amino acids called glycine, proline, hydroxyproline, and hydroxylysine. And basically what collagen is very simply is ground up skin or ground up ligaments and tendons and all the chewy bits of animals, and they grind them up into a powder. Gelatin is a less ground up or processed, rather powder than collagen, but which is why gelatin makes things more jelly-like, and collagen powder or collagen hydrolysate stays liquid as when you use it. Anyway, back to the actual paper. The reason that they're doing this, right, is that they're taking, quite simply, think of this: if we want to try and recover or grow tendons and ligaments, could we take tendons and ligaments from elsewhere, grind them up, and then supplement them? And then the building blocks of those tendons and ligaments, could they find their way into our tendons and ligaments or augment their recovery? That's kind of what they're looking really at. That's the basis of it. Can we supply the building blocks and maybe some more of the building blocks, these peptide chains, which I'll speak about, to ligaments during the training, and would this have an effect? So as Keith Barr says in an interview on Sigma Nutrition Radio, he says, and so the subjects, they jump rope for 6 minutes, and then they take a 6-hour rest, and then they drink whatever supplement they're supposed to drink again, and then an hour later they jump rope, and they keep doing this 3 times a day for 3 days. And what we find is that anybody who jumps rope, those people who jump rope, show a doubling in their collagen synthesis. And most of this collagen is synthesized from the bone, and that's from the impact of the jump rope. When we add gelatin, the low-dose gelatin wasn't enough to get a significant effect of the supplement. But when we increase the gelatin content in the supplement to 15 grams of gelatin, what we see is a further doubling of collagen synthesis. So what this study, well, the study data supported their hypothesis that starting an exercise bout 1 hour after consuming 15 grams of gelatin with vitamin C resulted in a greater collagen synthesis in the recovery period following exercise. Now, in the specific data, it is important to point out that this data reflected bone collagen synthesis in the subjects. But there was a similar response in the engineered ligaments in vitro treated with the same serum. So what we have here from this 2016 paper is that by supplying gelatin before training, it appears to augment collagen synthesis in the recovery period better than if you didn't. Now, that was really just the starter. So I want to give you a little bit more background here on collagen and what the extracellular matrix is, etc., etc. So basically, the structures of your muscle are individually bound together by what is called the extracellular matrix, and it's this collagenous vasoelastic soft tissue, right? It's kind of a lattice of connective tissue, this soft connective tissue, and it contributes to the stability and passive stiffness and the tensile strength. So this is the strength when it's under resistance and before it breaks. And also, more importantly, this lateral force transmission across muscle fibers and fascicles. So cross-linked collagen fibers within this extracellular matrix form a lattice, which in the case of the outermost epimysium, and I'm going to show you a diagram next, become denser and align unidirectionally to form a tendon attaching muscle to bone. So what we have here is this epimysium. So this white tissue, this is this connective tissue. If you ever eat any sirloin steak and stuff, you'll see the connective tissue running through along with the fat. But basically, so these fibers, these collagen fibers, all start aligning and getting bunched more and more tightly together as they then form this tendon going onto the bone. So if you remember, tendons join muscles to bones and ligaments join bones to bones. So what's very interesting about this is that many people understand that muscles develop force longitudinally, right? So that muscle is going to contract and shorten, and that's what drives. So the muscle fiber, the sarcomeres, the muscle fibers, all of these things then contract, become shorter, and that's what then drives the movement or the force on the muscle, right? So that's longitudinally. So if you can imagine that this is a bicep, it becomes shorter, and then the muscle moves across the joint. So as I said, so muscle fibers develop longitudinally by shortening, sliding filament theory of the contractile elements. So those are the sarcomeres within the muscle fibers. The muscle fibers are called myocytes. But what a lot of people don't realize is that 80% of that force is transmitted laterally into the surrounding extracellular matrix. And the function of this transfer is to allow the working muscles to continue shortening and to join adjacent fibers together to protect them from individual injury. So you have this contraction this way, longitudinally, but the force is actually transmitted laterally into this other connective tissue, this ECM. And this is important not just for allowing the muscle fibers to continue to do their work, but also this is how the force gets transferred all the way down through the connective tissue to the bone to move the bone across the joint. Or here you can actually see it better, because this connective tissue, this ECM, forms around every one of these little basically parts or sections of the muscle. So you can see here in this separate diagram that the tendon actually runs through the muscle all the way along, right through. So it's not just a case that you have a muscle belly and then right at the end of it you have this connective tissue, but rather connective tissue is running right through the muscle. And again, the point of it is the fact that it is providing the muscle's structural stability, passive stiffness, tensile strength, and things like that. So I've said here, and I've highlighted it, muscular strength and power is then determined by the optimal transfer of the generated force out and through the ECM and tendon, leading to movement across the joint. The structural properties, collagen type, alignment, density, cross-linking of the muscle ECM tendon complex is then essential to efficient force transfer. So what I'm saying is that we tend to think of collagen, the connective tissue, ligaments and tendons being one thing and muscles being the other. But they're not really. They are certainly the muscular tendon unit is one thing. And so the health of the collagenous tissue is going to affect the performance of the muscle. So here we have the structure of a tendon, and it's very similar to the muscle. It just becomes smaller and smaller until we get these fibrils, and then these fibrils then are the smallest unit of them are these collagen molecules, and these collagen molecules are cross-linked with various different glycoproteins and glycation end products and things like that. But I'm not going to talk about that in this little slide share, presentation. That you can go look at my article, because I spent a lot of time writing a lot of stuff on there about all that. So this picture is from Eric Horst's book, and you should, as a climber, you should be pretty familiar with this, right? So your fingers are flexed and extended by long tendons running from your forearm, right, through ligament rings, acting like pulleys. And when we talk about these pulley ruptures or pulley tears, this is what's happening here, right? The force that's being generated is pulling like a bowstring, right? So it's pulling down like a bowstring, causing damage. And this can be done for a variety of reasons. For instance, just conditioning. Somebody who's been climbing for 10 years is going to have much greater condition in their ligaments, their pulley ligaments, than somebody who's only been climbing a year. This is why they can pull harder. And we all know that your muscles seem to grow much quicker than your ligaments. And this is a good thing. Otherwise, if we could grow and hypertrophy ligaments and tendons, we would look really weird and probably wouldn't be able to use any of our joints. So as I've said here, this is just to highlight. I'm not going to read the whole thing, but basically what you've got to understand here is that the force acting on the fingertips is, you're looking about 300 to 350 newtons, right? The weight of an apple, or sorry, the force of a 100-gram apple on your hand, if you have an apple in your hand, gravity pulling it down, is 1 Newton. So what you've got to realize is, purely in the application of finger conditioning, ligament and tendon health is really an essential part of your climbing longevity. And training is going to improve as any stress on the body improves the condition of what is ever being stressed, up to a point. If you overstress it, then you get damage, which is what you see here. But if you don't stress it, it doesn't drive the adaptation of the tissue. So over time, as you're training, you're sending a signal to the ligaments and the tissues to lay down more collagen, to align the collagen in a certain way, and to grow within reason to get stronger. If you leave it and don't do any training, it atrophies. The same way with muscles. If you train progressively with muscles, your muscles grow bigger and stronger. If you sit in a bed for the next year, your muscles will atrophy. It's very much a use it or lose it. But use it too much and too fast and incorrectly, and you cause yourself damage. The point of all this, I'm saying, is trying to ramp up the reason why a nutritional intervention that is going to aid you with your training effect, your training stimulus, and is going to aid the recovery of your tissues is so important. So collagen fibers, right? We have muscle fibers. They get smaller. Muscle fibers then go into the tendon, right? The collagen fibers then get even smaller all the way to the collagen molecules, and then the collagen molecules are made up of amino acid chains or peptides. And it's these repeating amino acids, glycine, proline, hydroxyproline, that make up collagen molecules. So collagen, it is the most abundant protein in the body, and it makes up about 25% of your total protein mass. You have 45 distinct genes in the genome that code for 28 different types of collagen. 80–90% of the collagen in the body is type 1, 2, and 3, and yet they all serve to provide tensile strength and prevent overstretching. So type 1 is the most abundant collagen. That's the one that you're finding in tendons, ligaments, and joint capsules, cartilage, skin, bones, etc. Type 2 makes up 50% of cartilage, and then type 3 supports the walls of the intestinal tract, uterus, and your blood vessels. It's everywhere. So collagen proteins consist of 3 coiled peptide chains, each 150 amino acids long. So again, amino acids are the building blocks of proteins. And so collagen, these peptide chains wind around each other to form right-handed triple helix. So these coiled structures arise from the abundance of these amino acids that repeat: glycine, proline, and hydroxyproline. And they repeat hundreds of times in a sequence of glycine proline X or glycine X hydroxyproline, where X is any amino acid other than glycine, proline, and hydroxyproline, or tryptophan. Type 1 collagen molecules pack side by side and cross-link at their ends to form fibrils. And these have incredible strength. Gram for gram, their type 1 collagen is stronger than steel. And as I say here, again, all proteins are composed of specifically twist-folded chains of peptides or amino acids. The function of a protein is the way that it's folded. It's the way these amino acids come together and then fold in a certain shape. When you cook proteins, like an egg, they change the function, and they become different shapes, and they no longer can do their function. Hence, you can't make a cooked egg back to a liquid. So amino acids are both the building blocks of peptides, those are the building blocks of proteins, but they also, more importantly, act as signaling molecules. So, for example, the amino acid leucine activates other key signaling proteins, mTOR pathway, which is responsible for synthesizing new proteins. Now, I'm not going to talk very much about, or any more about protein specifically. I think best thing to do is actually go and listen to the podcast that I did with Brian Rigby of Climbing Nutrition. If you search in your podcast software for the Climb Side podcast, episode 1, we talk for about, I think, 2 hours on protein and the importance of this. But basically, I say a low protein, low varied amino acid diet is then suboptimal for growth and recovery. So now this is where it gets interesting with this nutritional intervention. So a paper came out in 2009 that talked about the synthesis of collagen and the amount of glycine that is required, and that there, as I've highlighted here, the amount needed for all metabolic uses, including collagen synthesis, is about 10 grams per day in a 70 kilogram human. And the reason that this is interesting is that there seems to be a discrepancy between how much we can produce endogenously and actually how much we need. And the reason I present this is because if you require, as I'm saying here, so your total glycine production, so let's go back here if you are a little bit confused. So remember, collagen is made out of these amino acids, glycine, proline, and hydroxyproline, which repeat. So we're looking at the glycine. So glycine is the predominant amino acid in collagen, and that's why it's so important here. So what the paper found was that the total glycine production per day is 3 grams. Glycine that's derived from dietary protein, so that's hydrolysis of the protein that you're consuming per day, is 2.5 grams, right? The expenditure, or basically the requirements of the body for glycine, so in this, we've got these porphyrins, purines, and creatine, so that's another, glycine is part of creatine synthesis. Glutathione is a antioxidant, bile salts there for digesting fats, is 1.5 grams per day. And then for collagen synthesis, we're looking at for skeleton, so that's the bones, 5.6 grams per day, muscle, 5.10 grams per day, and then skin, cartilage, ligaments, etc., 1.34 grams per day. So what we have here is that this is roughly 12 something grams a day of collagen that we require. The glycine production of the body is 3 grams per day. And in a typical diet, you get about 2.5 grams of glycine per day. So as they're saying here, the amount of glycine available for synthesis, about 3 grams a day, together with available from the diet in the range of 1.5 to 3 grams per day, may fall significantly short of the amount needed for all metabolic uses, including collagen synthesis, by about 10 grams per day for a 70-kilo human. And so they're saying here, this result supports earlier suggestions in the literature that glycine is a semi-essential amino acid and that it should be taken as a nutritional supplement to guarantee healthy metabolism. Quite simply, in a well-formulated diet, you're going to be riding the fine edge of glycine requirements. And remember, the body is always going to prioritize what it manufactures or recovers. So the reason I'm doing this is that the importance for climbers for having an optimal nutrition is for the recovery of your muscles, but also the recovery of your connective tissues, since we hang off our tissues all the time. And we're not just talking about fingers, we're talking about elbows and shoulders, right? In the most part. So if your diet is low on glycine coming from your diet, say you have a potentially low protein diet, so your glycine that's coming from protein is low already, and you are yanking on your joints and tendons every day, you may not be recovering or growing and conditioning your connective tissues optimally, because they won't be prioritized as such. If that makes sense. So let's do a little bit of overview here. So I said here, the generation, transfer, and expression of muscular strength and power is not isolated to muscle tissue alone, but rather the whole muscle connective tissue complex, which includes the collagenous intramuscular matrix and tendon unit. Soft tissue, muscle, tendon, ligament, tensile strength, breaking strength, control stability, and force transfer are influenced by the tissue collagen content, collagen cross-linking, and a resulting stiffness or compliance of the tissue. Now, in my article, I go into more detail on those points and how tissues become more compliant and stiff, and why you would want it to be stiffer near the bone and more compliant in the muscle belly, and how training impacts that. Actually, I don't even think I put the training bit on the article yet. That's a whole nother section that needs to be added. But I will do another talk on that at some point. Muscle fibers transmit 80% of their contractile force laterally to the surrounding collagen layer, 20% longitudinally towards tendon, and research has shown that the amount of lateral transfer can increase the muscle strength relative to muscle size. This is a really key point. As climbers, we don't want big, bulky muscles, but what we can do is we can actually increase the force transfer in the muscle, despite not increasing the muscle size, by improving the quality and the conditioning of the connective tissue. That is going to be augmented by specific types of training, but also by what you're providing in the diet that's going to help it recover. In my article, I talk about things like advanced glycation end products. I talk about how proteins and specifically collagen can be affected by glycation, so that's high sugar, but I'm not going to go into that right now. Connective tissues are highly hydrated and behave like water when loaded at velocity, and stiff and responding elastically when loaded fast, compliant and absorbing force when loaded slowly. So if you can imagine smacking water, it responds back very hard. But if you go into water, slip into water slowly, it is compliant. It's a similar thing. Because connective tissues are so hydrated, that's how they actually perform, which is why when you do plyometric type movements, or when you climb with a sense of bounce, you have more force. It's because they're elastic. So that's why it's more energy efficient to become more elastic in that sense. So yeah, connective tissues adapt to increase loading by both degrading and increasing collagen content, quality, and cross-linking. Disuse leads to a decrease in total collagen content. As I said, use it or lose it. And also, the way you train is going to improve how the collagen aligns itself. Disuse causes or allows collagen to become stiffer in the muscle. Think of it like this: if you have a muscle that has this collagen, this extracellular matrix running through it, and you don't use it, then this collagen will degrade, but also it will become stiff and incompliant within the muscle belly. And the tissue, the extracellular matrix, collagenous tissue that is approaching the bone from the end of the muscle will become lax because it's not being used. And what happens is you then have a muscle that is stiff collageneously and a join of the tendon to the bone that becomes soft. So straight away you have a problem with force transfer there. What you want is the very opposite. And the opposite is created by allowing the tissues to be used, so the muscle belly to be used. That breaks down collagen and allows it to align and become pliable because it's continually moving. And the force that gets generated from that muscle to the bone causes a stress on the collagen that's reaching the bone, the tendon, and that force causes the collagen to align and to cross-link in a certain pattern to become stronger and stiffer. And that's what you want. You want stiff, strong tendons coming into the bone, and you want soft, pliable, collagenous tissue in the muscle belly. So, training. So I said here, resistance training favors positive soft tissue adaptations, including increased cellular growth and remodeling, increased enzymatic collagen cross-linking, decreased glycated end products, so that's the AGs, which I talk about, maintaining tissue compliance near the muscle and stiffness nearer the bone, leading to improved performance and muscular energy efficiency. Resistance training releases a biochemical cocktail of hormones and growth factors that support the growth and repair of soft tissues, even if they're not trained directly themselves, highlighting the importance of continuing to train around injuries for their recovery. But as an aside, because some people might have heard this, and it needs to be corrected. There was a notion back in the early 2000s that if you were to train your legs first, so big muscles, you would release different hormones like growth hormone that then would float around and could be used when you're training your arms. And so the thought was that if you increase these anabolic hormones by doing heavy leg sets before you do any of your bicep curls, you could augment the growth of your biceps better. This has been proved incorrect, and yes, I'm not going to go into much details, but that's not true. It has no effect in terms of growth on your muscles. So train how you like. Don't think that training legs first is going to make your muscles on your arms grow because of the hormone release. Anyway, back to this. So I said in comparison, and this is the interesting bit now, in comparison to muscle tissue, connective tissue is less sensitive to differences, stress strain levels, or contraction type, concentric, isometric, and eccentric. Thus, certain training modes may lead to an unbalanced adaptation of muscle versus tendon. Now, I want to do a whole nother slide and talk about different training modalities that is related to these three elements. Concentric is a muscle shortening. So think of a bicep curl. Isometric is the holding. So isometric would be holding the dumbbell in your arm without letting it drop or bringing it closer to your body. And eccentric is the lowering portion of it. And these three have an impact on the muscle development and strength and force. And quite simply, you shouldn't just train one of them. But I will explain more of that another time. Eccentric training appears to have a greater potential than concentric training to increase collagen growth factors in muscle and lateral force transmission, which may be due to the greater eccentric force production or local shear stress in muscle tissue. That is what we're doing, is if you can think about doing movements in the eccentric mode. So now, this is the tricky thing, and I don't want to go into too much detail, but basically, if you were to do pull-ups and you do the lowering portion of your pull-up very slowly, you get fatigued very quickly, and also you'll probably generally have more muscle soreness the next couple of days because there is more shear stress on the muscle tissue because it's under load for longer. But true eccentric training is training with a weight that you cannot lift yourself, in, say, the case of a pull-up, concentrically. So, for instance, my 1 rep max for a pull-up is about 45 kilos. So I can barely do one pull-up with 45 kilos around my waist. I weigh 77 kilos at the moment. But what I can do is I can get up on a step, get to the top of the pull-up position, and lower myself down slowly with 45 kilos to the bottom, and then walk up the step again, get to the top of the pull-up position, and lower myself slowly. Eccentric training will always allow you to actually manage more weight than you can concentrically. But that's just that's a little training freebie there. Something to think about. As I say here, training after injury should begin as soon as possible with limited weight exercise, as the amplitude of load is not important for stimulating collagen production. Look, this is an interesting thing. So, and I want to try and flesh this out a little bit more in my article update at some point. But it appears that just using tendons actually causes them to grow, and you don't necessarily have to increase the amplitude of load, which flies in the face of some data on how you're supposed to put the stimulus. But I need to get more clarity on this, so I'm going to leave comment as is. This is an interesting bit. So a lot of people don't realize this, but connective tissue cells respond to a training stimulus of less than 10 minutes before requiring 6 hours of rest. Focused connective tissue training should then be performed 6 hours before or after other training and limited to less than 10 minutes of loading. There's potential for 3 training sessions per day. So this you may not have heard of unless you follow my Instagram feed. This is from Keith Barr. Keith Barr actually emailed me this back in 2016. And what it is that the adaptation of the training effect, the adaptation of muscles to the training effect is much, much longer than the adaptation of connective tissue to the training effect. So what that means is that you will do a resistance training protocol. So let's say you're doing pull-ups, right? on the hangboard. Your muscles will continue to respond to that training signal for 24 hours. There will be an acute spike, but then it will continue on, and your muscle fibers will grow and recover on that from that training stimulus. Your tendons and your ligaments in your hands won't, though. They will stop their growth and recovery biochemicals changes in less than 10 minutes. And any other stimulus that you provide to those tissues don't promote the growth, they just fatigue the tissue. This is kind of confusing, but think of it like this. If after, and think of it in terms of a cumulative load, if you were to climb for, let's say, 2 hours, and each of those, let's say in a bouldering session, each bouldering problem is normally like 10, 15 seconds of climbing the most, if that. If you were to somehow add up all the loading that you do on a specific ligament of one finger, you're probably going to see that that is going to be, let's say, a cumulative time of 10, 20 minutes in total, even though you've been climbing for 2 hours or longer, right? So it's a cumulative load. What research has said, or has shown, this is Keith Barr's work as well, is that after 10 minutes of cumulative load on tendons and ligaments, they shut down. They don't continue to adapt, whereas muscle tissue continues to adapt. And so the point of this is that, say you've been climbing for whatever, 2 hours, and then you think that you're going to do some tendon ligament fingerboard training, right? No doubt hanging off, doing dead hangs after your 2 hours of bouldering is going to impact the musculature of your forearms and shoulders, etc., by your dead hangs, and some of the muscles in the hands, because they can continue to have a stimulus. What I don't believe is going to happen is that you're going to provide any benefit to your tendons and ligaments. Because if your tendons and ligaments have had 10 minutes of loading from your climbing, then all they are going to be is fatigued and damaged by adding dead hang training after a climbing session. I think if you want to do climbing, dead or finger training specifically, then you should do it before you're climbing, if that's, or away from climbing, or as a separate session. But the point being is I just don't see any point of anyone doing finger training after a climbing session. That's all I'm saying, really. I think it's just going to set you up for damage. So anyway, I said here, if loading specific tendons and ligaments, i.e. finger training, be aware that the growth adaptations turn off after 10 minutes of cumulative load. Specifically, loading the tissues greater than 10 minutes will not drive any further growth, but will increase fatigue and potential for injury. And this is the interesting thing. The loaded tissues, right, require 6 hours of recovery before being responsive again. So your tendons, after you've hit this peak of growth signaling, will turn off, and they actually require 6 hours before you can give them another stimulus to grow. This is not a particularly bad news, right? If you were to maximize your finger training protocol, then what you do is you would train, let's say, first thing in the morning for a cumulative under 10 minutes of loading. Now, if you're doing dead hang sessions, it doesn't mean that your dead hang session needs to be less than 10 minutes. What it means is that as you're calculating how long you're loading, you're hanging on your fingers, just make sure that all those repeaters, or whatever you want to call them, don't go over the 10-minute mark, because once you pass 10 minutes of cumulative load, you're just wasting your time and getting fatigued. Then you can go about your day and maybe do another session 6 hours later and do the same thing. And then 6 hours later from there and do the same thing. And that way you could actually potentially be the most optimal way of training your fingers, basically three sessions a day. And this is not even talking yet about the nutritional intervention, which I'm going to talk about next. Obviously, all this stuff works for other joints and ligaments in the body, right? Not just fingers. But I just want to give you something to think about on that. Diet, right. So this is now going to explain a little bit more. So muscle tissues are richly supplied with blood. The window for adaptation, growth, recovery is extensive, lasting greater than 24 hours post-training, extended 3 to 6 hours after protein ingestion. So that's going back to that amino acids and them being signaling molecules. So leucine is the primary one here, and optimized by a total daily protein intake and protein dose distribution, right? So I actually don't have it on this slide, but as we spoke about in the Climb Side podcast, episode 1, protein, you're looking at really about minimum of about 1.6 grams per kilogram of your body weight, protein per day. And that's split into meals of about 30 grams per meal. And you can go upwards to about 2 grams per day. Oh, I do have it here, highlighted. Connective tissue, so tendons and ligaments, are poorly supplied with blood, behave like sponges when loaded, and the window for adaptation is very small, peaking less than 10 minutes post-training, turning off 1 hour later, requiring 6 hours of recovery before becoming responsive to training again. And I say here, probably optimized by absorbing the amino acids, including leucine, glycine, proline, and potentially collagen peptides, hydroxyproline, in circulation during the training window. This goes to Keith Barr's work, right? So what I say here is consuming 25 grams of whole protein, so like i.e. whey protein, but if you had to have a typical size chicken breast, you're getting about 40 grams of high quality protein, with an additional 15 grams of gelatin or collagen hydrolysate, either or, and 200 milligrams of vitamin C. Now, this is a very small amount of vitamin C, but vitamin C is a cofactor that allows the bonding of the molecules of collagen. On my article, that goes into more detail. 30 grams of carbohydrate is just for energy, not necessary, but having that allows you to have an energy substrate into your system if you're coming from, say, not eating for the last 2 hours. So what I'm saying here is muscles are supplied with blood continually. Tendons are not. They're like sponges. So what they do is they absorb the surrounding plasma. So the whole point of this is that 30 to 60 minutes, but probably around about 30, before training, this, depending on what you're eating, because it's to do with digestion rates and absorption into your bloodstream, 30 to 60 minutes before any training sessions, and this can be your finger training, your finger training sessions, your dead hang sessions, consume a scoop of whey, right, your whey shake, or a equivalent vegan, vegetarian, plant-based protein shake with 15 grams of gelatin. Actually, if you're consuming a vegan, vegetarian protein, you don't want to be using 15 grams of gelatin because there is no such thing as vegan sourced or plant sourced gelatin. There is plant sourced glycine, but unfortunately you cannot get gelatin which is going to contain glycine plus these other things called hydroxyproline. This doesn't unfortunately exist in the plant kingdom that I'm aware of. Well, certainly collagen peptides are made from collagen, and collagen doesn't exist in plants. So that's one tip before you do any of your training. Protein, gelatin, and a little bit of vitamin C. You could have a glass of orange juice if you wanted to dissolve it into a glass of orange juice if you want. What you don't want to do, which is a separate matter, and Brian and I will talk about this on the Climb Side podcast, is megadosing vitamin C or antioxidants around your training is going to actually hamper your training because you are removing the part of the biochemical stimulus for adaptation. So don't take high dose vitamin C before you're training, but about 50 to 200 milligrams of vitamin C is going to be fine. And it's just a little extra that you can add in this little stack here. But saying that, this is the kind of cherry on top. This is what's going to be the most important thing for your growth and recovery, as we stipulated on the Climb Side podcast. Consuming 1.6 to 2 grams of high quality protein per day is going to be the greatest thing you can do for muscle strength and recovery from your training stimulus. But, and this is where I think is really important, actually, going back to that slide talking about the requirements for glycine per day, adding an addition of 10 grams of glycine per day, and you can factor in the gelatin as well, but it's not a big issue. There's no toxicity to high levels of glycine. So for instance, you can get 5 grams of glycine from gelatin and 10 grams from just pure glycine. I say here would be the best consistent dietary practice for supporting overall soft tissue, muscle, tendon, ligament health. Sorry. So what I'm saying is that you're going to get some glycine from here if your protein quality is good. But I really think that climbers would benefit from buying gelatin or collagen, which they then can use to get 10 grams of glycine per day. So I think you're looking at about, actually I have it on the next slide, I think you're looking at about 2 to 3 grams of glycine per 15 grams of gelatin. So you could do the maths if you just wanted to buy gelatin or collagen to supplement to try and reach that 10 grams. But what I do is I have both. I have collagen powder for my collagen before training, and I have pure glycine powder to have daily. As I say here, if you are not vegan, then eat more stews and not just muscle meats. So obviously, if you're cooking meat that is collagenous, so things like beef cheeks and what they call offcuts, then when you cook it, all that collagen is going to be transferred into your stew, and then you eat that and you're going to be able to get a lot of high quality collagen and glycine. Interesting enough, brown rice protein powder is a very rich source of glycine, but vegan glycine does exist. I think now Foods does a vegan sourced glycine because it's an amino acid, and you can get amino acids that are plant sourced. A lot of the amino acids that you buy, like your BCAA powders and things like that, are actually made out of things like feathers, and are actually animal derived. I think they can do some of them synthetically, but yeah, most of them are going to be ground up feathers and things to produce. Just so you know. But if you wanted to get glycine, you're going to get a high amount in your brown rice protein powder. But again, you can get just glycine freely that's vegan sourced. So here's an example of what I do personally. So on a typical day, I get up about 6:30 in the morning and then get to the gym for about 7. And I don't actually eat anything before I go to the gym. If I'm doing morning training, it's such a short training thing. I don't find that I need anything. And as we'll talk about in the Climb Side podcast, there is benefits in training fasted. But post-workout, what I do is I take a scoop of whey, and with which has got 5 grams of glycine that I've added in, right? And then I have my normal day's meals, and I just make sure that I get my 30 to 40 grams of protein per meal. So that's whatever, breakfast, lunch, and dinner. And then just before I jump into bed, I take another scoop of protein with 5 grams of glycine added. Now, glycine is not just for collagenous tissue growth. Glycine is a very interesting amino acid, and maybe I'll do another whole talk on glycine, its effect on metabolism things and other processes in the body. Yeah, yes, don't, this, funny enough, will actually help you sleep as well. So you'll find that your sleep is pretty good if you have 5 grams of glycine before bed. Anyway, so that's what I do on my typical day. On a climbing specific day, so like either for me it tends to be a Tuesday or on the weekend, if I get up and want to get up and do a gym session before work, then I normally do cardio on the climbing day for obvious reasons. Don't want to tire my arms out before I go for the climbing later. What I do is I do the same sort of thing, whey and glycine post session. Then I have my kind of 2 meals, 30-40 grams of protein. Now, obviously, I'm not putting in carbs and fats here, but this is just talking about the protein part of it. And then immediately before I do my climbing, so normally I take this just before I jump on the tube, I have a scoop of whey protein with 15 grams of collagen. And so by the time I start doing my warm-up and start doing my training, I have these circulating amino acids and collagen peptides in my plasma, which then can be absorbed into my tendons and ligaments. That's the point. That's the point of this whole talk. Post-climbing, a meal, 30-40 grams of protein. And then just before bed again, I have my heaped scoop of whey and 5 grams of glycine. So that's basically what I do, and what I think is a very useful practice to do. So yeah, so I hope that was interesting. I did not prepare this very long, so I put these slides together after a personal training client, and then I thought I would quickly run through this. The article that I have on my website, so my website is useful.coach, and the article is called Nutrition for Soft Tissue Training, Recovery, Injury Prevention. And basically, it's a kind of very long, detailed explanation of a lot of this, with more to come when I have time to do it. I have a podcast, as I said, with Brian Rigby of Climbing Nutrition, where we talk much like this for a couple of hours about protein, carbohydrate, and fats. The protein and the carbohydrate podcasts are really good, and they should be very useful for you and give you a lot to think about. Just search for ClimbSci in iTunes, etc., or you can go to climbsci.com. I am London-based, and most of the time I'm at the Arch Climbing Walls in Bermondsey. But if you have any questions about this, you can ping me an email on tom@usefulcoach, or you can find me on Instagram at usefulcoach, or Facebook, usefulcoach. And so, yeah, so that's my climbing and collagen, a cheap and potentially effective nutritional practice for augmenting tendon and ligament strength and recovery. Oh, one thing I wanted to show you. Yeah, which I missed this slide somehow. This is the amino acid composition of collagen versus whey. So one of the reasons that you can't just eat collagen as a protein source is that it has no leucine. Leucine is the one amino acid that you won't find in collagen. So if you're trying to grow muscles by eating a cheap protein source like collagen, you're not going to be so optimal. What you can see, though, is that in whey protein, you have an abundance of leucine. This is per 30 grams is a typical scoop, right? So a typical scoop of whey protein, you have a roughly 2 and a bit grams of leucine, which is optimal in stimulating muscle protein synthesis. You can see there's a very little glycine in whey protein. So in collagen, we add collagen powder to our whey protein shake, and what do we get? We get this nice spike of glycine, right? So just over 3 grams per tablespoon. And we get these other peptides, which you don't find in whey at all, such as hydroxylysine and hydroxyproline, right? These are these peptide chains which we think are actually doing a lot of the work with collagen/gelatin supplementation. So yeah, so that's just the last slide. So I hope that you find this very interesting. So please share, and if need be, I can do another presentation like this on more detail on something. But yeah, my name is Tom Herbert, and you can find me on useful.coach.